Okay, so in this video we're going to talk about vector equations of lines. The vector equation of a line in 2 or 3 dimensions can be written as r equals a plus tb, which is sort of like y equals b plus mx. The t is like your x here. A is the position vector of any fixed point on the line. It doesn't have to be an intercept. It could be any point that's on the line. And b is a different vector. The b vector here tells you the direction vector, or the direction that this line is headed in. You can think about it as the slope, or it's any vector that's parallel to the line that tells you the direction that it's headed in. So if I was to write an example, it would be something like r equals, I like to write these vertically, so here might be a point on the line, and the direction vector tells you from that point, you can head -1 in the horizontal direction, 3 in the vertical direction to get to another point on the line. So it's a little confusing in the visual below, but basically what's happening is if you substitute a constant in for t, you'll get a point for r. So that's the series of points that lie on the line r. So t is like a scalar, you plug something in, and out for r you get a point, and all those points together make the line r. Here's a really simple example. Find a vector equation of a line that contains that given point and is parallel to that given vector. So we have a point on the line, we have the direction of the vector. So to put it all together and write it as an equation, you can write it vertically. You could also write them horizontally if you prefer. I just think it's a little bit easier to see them this way. And that would be it. So the point that's on the line is the one that's given -1, 3, 0. The direction vector is 3, -2, 1. I got that from the component there of vector v. To write that one horizontally, that would be the point, and that would be the direction vector. I just wanted to show you can write it that way. I tend not to, but you might see it written that way in an exam question. Find a vector equation of the line passing through the 2 points, so taking it up a level. So now we're it's giving us 2 points and asking us to write the vector equation of the line. So the first thing we're going to want to figure out is the direction vector. So the direction vector from A to B, how far do we have to travel in the horizontal direction? +4. In the vertical direction, looks like -5. So that is our direction vector. And so we're ready to write our vector equation of the line. You can use either point that's given that's on it. I use 2, 7, and the direction vector is 4, -5. One thing you might be asked to do with the vector equation of a line is write it as a regular linear equation if it's in 2 dimensions like this one is. You could write this as y equals mx plus b, or standard form ax plus by equals c. The one thing you'll need to know, or you might want to use, is the notion of this vector, which tells you the direction of the line, means that the line has a slope on the regular coordinate plane. If you think about 4, -5 as a vector, that means the horizontal change is +4, the vertical change is -5, and slope, as we know, is vertical change over horizontal. So the slope of this line is actually -5/4, which you could then use in like y equals mx plus b if you were trying to write this line in slope-intercept form or standard form. For the point, you could use any of the points that's given to you, you could use as a point, and then use that to solve for the y-intercept. One thing you'll be asked to do with vector equations of lines is determine if lines are intersecting, parallel, or skew. So once we're in 3 dimensions, not only can lines be intersecting, which means they cross, or parallel, which means they never cross and are going the same direction, but they could also be skew, which are 2 lines that never cross and aren't going the same direction, as in this third picture here. So line L is totally above line M in the 3 space, so it's never going to cross line M, even though they're not going the same direction. M is going to pass underneath line L and never actually intersect with it. There's a lot of information on this slide. The examples on the next few slides will make this a little bit clearer, but we can talk through it here. So first we want to know, how can I check if 2 lines are parallel if they're given to me as vector equations? If the direction vectors are parallel, then the lines are parallel. And what we know about parallel vectors is that one is a scalar multiple of the other. So if I have a line with direction vector 2, 4, and another line whose direction vector is 4, 8, then those 2 lines are going the same way, right? Their direction vectors are scalar multiples of one another. So therefore, those lines are going the same way, parallel. In red, there's an alternate way to find it. We're not going to bother with that one. Underneath what's in red, it says check also if they are coincident lines. This means not only are they going the same direction, but all the points are actually the same, which would mean that they're actually the same line, just written two different ways, right? Same line twice. To check if they're coincident, you just want to see if the given point from one line is actually on the other line. Because if they have points in common and they go the same direction, then they're actually the same line, not just parallel, but in fact coincident. If you've ruled out parallel and coincident, now we're on the bottom of this screen, then we're checking to see if the lines are intersecting or are they skew. And in order to do that, you're going to set up a system of equations and find the point of intersection, which is what we're going to do on the next slide. So here's an example. Parallel, coincident, intersecting, or skew. First thing to check is their direction vectors. Are they scalar multiples of each other? We can see here clearly they are not. So these lines are not parallel. They're clearly not the same line. They don't even go the same direction. So we're really checking here to see if they're intersecting or skew. So my recommended method for that is to write L1 in vertical form. It's going to be easier for us to pull out the system of equations if it's written in vertical form. And then write L2 similarly, but change the variable t to be something else. It's really common to see s used, so I'm going to use s. The reason being, we don't know if these lines actually have the same n intersection point. We don't know if they have a point that lies on both of them. So we want to change the variable and not assume that there's the same t value that would lead to the same r value. And then we're going to pull out each component as its own equation. So the x component, the y component, and the z component as its own equation. So the horizontal, or the x component from the first line is 1 plus 4t. We're going to set that equal to the x component from the second line, 2 plus 8s. Then we're going to do the same thing for the y component. For the first line, that's 5 plus negative 4t. And for the second line, that's 4 plus negative 3s. And for the z component, trying to be really careful in setting these up. Okay, so there's our three equations that we're going to use to solve to see if these things are intersecting. What I'd like to point out is that there are three equations in this system, but only two variables that we're solving for, and that's how this will always be. You'll always have three equations if it's a 3D line, and only two variables, the s and the t. So what we're going to do is use two of the equations to solve for s and t, and then we'll use the third equation to check. So I'll use the first two equations since none of these are simpler than any of the other ones. I'll use the first two equations. I'll use the elimination method because I can see that they're pretty well set up for the elimination method. The t's are actually already set to cancel. Let's get this out of the way. Minus 3s. Okay, so the t's will cancel. I'll have 6 equals 6 plus 5s. 6 minus 6 is 0. 0 equals 5s. Therefore, 0 equals s. All right, so I've solved for s is 0. I will plug that back into, let's say, equation 1. Doesn't really matter which one you plug it into, as s in order to solve for t. T equals 1/4. All right, and then like I've said, I'll use the first two equations to solve and then the third equation to check. So I'm going to use the third equation to plug in the s and t that I obtained and see if these lines really do intersect there. Equals 5 plus 1 times 0. Here I can see that the left side of this equation is clearly not going to equal the right side of this equation. These are not equal. And therefore, these lines do not intersect at a common ST point. There is no point where both of these will have the same R output, if that makes sense. There's no input for the scalar that will give us the same R point. So therefore, these lines don't intersect, and they must be skew. We will see one where they are intersecting, so you can see what that looks like in the end as well. All right, so in each of the following, we're going to find the point of intersection of the two given lines, and if they don't intersect, we'll explain why. So in the first example up there, we want to check always if they're scalar multiples of each other, the direction vectors are, because then we have either parallel or coincident lines. We want to make sure we're always looking for that first. So looking at those two direction vectors, 4, 1, 0, and 12, 6, 3, I can see that one is not a scalar multiple of the other. Let me see if I can get this one out of the way. Give us a little more space. All right, one is not a scalar multiple of the other, therefore not parallel, not coincident. We're going to find the point of intersection. So set them up vertically. Makes it a little easier to pull out the system. Don't forget to change the variable for your second equation. Let's see if we can figure out where these lines intersect. So negative 1 plus 4t equals negative 13 plus 12s. 3 plus 1t equals 1 plus 6s. And 1 plus 0t, that's going to be a helpful one, equals 2 plus 3s. The reason that last equation is helpful, number 3, the z component, is because there is no t in it, actually. This term is gone. So I can actually use that equation very directly to solve for s. So 1 equals 2 plus 3s. Subtract 2 from both sides, divide by 3, and negative 1/3 equals s. I will substitute that back in to solve for t, maybe in the second equation. To label what I'm doing here, 3 plus t equals 1 plus 6. Substituting this in for s. So 3 plus t equals 1 minus 2. And t must equal negative 4. All right, so now I've solved for s and t. I'm going to use the first equation, which I haven't touched yet, to check. So I will use negative 4 as t. Negative 1 plus 4 times negative 4. Negative 13 plus 12 times negative 1/3, and see if these actually are equal. So negative 1 minus 8 on this, negative 1 minus 16, negative 17 on this side. And over here, negative 13 plus negative 4, negative 17 on this side. And that means these lines do intersect. Now, s and t are not the point where they intersect, right? Those are a scalar that you would substitute into each of these respective equations to find the point r on the line where they intersect. So you can substitute either the t value into the equation where you have t, which is this one, or the s value into the equation where you have s, which is this one. You don't need to plug it into both if you feel fairly confident in your work so far. You just need to plug one in to figure out the r, which is a point on the line. So I'll plug in negative 4 to the first equation. I find that a little bit easier. Negative 4 is the scalar that you're plugging in for t. That's what we got when we solved for it, which means you'll multiply negative 4 by the direction vector, take that result, add it to the given fixed point on the line, and you'll end up with the point negative 17, negative 1, 1. And so the point of intersection, written as x comma y comma z, is negative 17, negative 1, 1. And we don't need to do the final example. It ends up being another case where there's skew, which you can work out if you'd like. And that is all.